Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, you're in the right spot, so go ahead and click the subscribe button. That said, let's get into the current video. I'm going to talk about the derivative of a vector function. And what I'm going to do is show you geometrically how the derivative is related to the graph of the vector function, and then we'll talk about how to do computations of computing those derivatives. First and foremost, let me take a look at a property of vectors. So let's say I've got two vectors in two space here. So let's say I've got, here's the vector, let's say u. And then let's say I've got a vector v. What I want to do is I want to see what does the relationship v minus u look like. So where is v minus u? What does the sketch of v minus u look like? How is it related to those two? Well, here's what I'm going to do. I'm going to ultimately, in order to do v minus u, I'm going to do v plus negative u, because negative u is just a reflection of the vector u, so it's going to be the same line segment just going in the opposite direction. And then to add those two vectors, we use the parallelogram law. So let me go ahead and take a look at what negative u would look like. Again, it's going to be the same length going along the same line segment, just in the opposite direction. So this right here, that looks about right. This would be the vector negative u. Okay, and then if I want to add v plus negative u, what I'm going to do is I'm going to plot the line that is parallel to v, but starts at the tip of negative u. And so it's going to look like, that looks pretty good. And then I'm going to draw the line that's parallel to negative u, but starts at the tip of v. And that would look like, let's see, what color did I use there? Okay. And then remember, to add v plus negative u, I use the parallelogram law, which means I start at the origin and the terminal point of the sum would be the intersection of those two line segments. So therefore, I would have the following. Let's see, what color do I want to use? Let's use this one. Okay, so that vector that I just did right here, this is v plus negative u, or of course v minus u. Now here's the one property of vectors, that I can slide them around as long as I don't change their length or direction, and they're equivalent vectors. So if I take this vector right here, I could actually slide it to right here. So this right here would be the vector v minus u. So the idea is it starts at the tip of u and terminates at the tip of v. I know those don't look like they're necessarily the same vector, but it sketches on a screen here, so bear with me. But the idea is, like, again, so the difference between these, v minus u, it starts at the tip of u and terminates at the tip of v. Okay, so now let's go ahead and take a look at how this is really going to illustrate the geometry of the derivative of a vector function. So, definition. The derivative of a vector function r of t, okay? So the derivative of a vector valued function r of t is given by the following. And just like in your Calc 1 course, it's going to be the same concept. It's the limit of a difference quotient. So it's going to be the limit as h approaches 0 of r of t plus h minus r of t all over h. Okay, And just like with Calc 1, there's a couple different notations we can use for this. The most common being Leibniz's notation, which would be dr dt, so the derivative. Or on the other hand, we can use prime notation, so r prime of t. Either one of those represents the same thing. Okay, well, let's take a look at the graph of a vector function and see how this difference quotient which would be related to this sketch up here. So let's go ahead and draw. I'm just going to use this one. So if you remember, the graph of a vector function consists of all of the terminal points of the output vectors, right? So if I have a vector, let's say r of t plus h and r of t. So let's say here's r of t plus h. So this is the vector r of t plus h. And then let's say I have a vector r of t. Remember that it's just the terminal points of those vectors that would constitute the graph of the function. So therefore, let's see, whatever this terminal point is here, terminal point is here. And so it's all those terminal points of all those output vectors. So maybe it looks something like, you know, and this right here could be, say, the graph of r of t. Okay. Now, how does this all tie together? Well, look in the definition of the derivative here. I've got the difference of two vectors, and up here we illustrated the geometry of the difference of two vectors. So r of t plus h minus r of t, the difference of those two is going to be the vector that starts at the terminal point of r of t, and it's going to terminate at the terminal point of this vector. So just like this guy right here, I'll go ahead and, oops, dropped a marker there. Go ahead and draw this vector here. That red vector is r of t plus h minus r of t. Okay. Now, dividing by this whole thing by h, this is equivalent to multiplying by 1 over h, which is simply multiplying the difference of these vectors by a constant. And what happens when I multiply a vector by a constant is we change its length. So what could happen to this red vector here if I multiply it by, you know, a constant bigger than 1, which of course if h is going to 0, let's say h is eventually a half. So dividing by a half would be equivalent to multiplying by 2. So I am making it a little bit longer in this case. So therefore this could be something like maybe that vector. So this would be the difference quotient in this case. So I'll just write this as a delta r over h. Okay, and the idea is as h goes to 0, these two terminal points are going to get closer and closer together, and what's going to happen as h goes to 0, this orange vector here is going to be tangent to the curve. And so if I draw this down here, if I redraw it, I have that same sort of curve here for r of t. What's going to happen is, let's say this is my point right here. Let's see what color I'll use. Let's try blue. Then the derivative is going to be tangent to the curve, which shouldn't be a surprise because back in Calc 1, the idea for a tangent line is the slope was the derivative, and that's how we got, again, something tangent to the curve. So same thing in this case for a vector function. To get something tangent to the curve, we compute the derivative. All right, so this just kind of illustrates the geometry of how the derivative of a vector function is related to the graph of the vector function. Now let's go through and compute some examples. Okay. Well, if I look at, again, the definition of the derivative, this is the limit of the difference quotient, but let's sort of analyze this expression right here. If I subtract vectors, remember we subtract corresponding components. If I take a vector and I multiply it by a constant, I distribute that constant through all the components. So the idea is if I'm going to take the difference of each component and then I'm going to divide each component by h, that results in just having the difference quotient in each component. And then I'm taking the limit of that, so the limit of the vector that has all the components are all difference quotients. That just means I'm going to differentiate each component function. In other words, if I have a vector function that looks like this, so r of t is equal to, let's say, t squared e to the negative t cosine t. To compute the derivative of that, okay, I just differentiate each component. So the derivative of t squared would be 2t. The derivative of e to the negative t would be negative e to the negative t. And the derivative of cosine, negative sine of t. Okay, simple as that. It's just Calc 1 skills. So in a Calc 3 class, primarily you're using Calc 1 skills. Another example. So let's say I wanted to differentiate a vector function of the form r of t is equal to, all right, let's say I've got the square root of t. Let's do t e to the 4t, and then I've got tan inverse of t. All right, compute the derivative of this vector function. dr dt is equal to, well, remember that the square root is the same thing as the 1/2 power, so off to the side here, the square root of t is the same thing as t to the 1/2. And the reason we want to think of it this way is because then we just reason through the power rule, right? So the square root of t being t to the 1/2, the power rule applied to that, its derivative would be 1/2 t to the negative 1/2. And certainly I could rewrite that expression so the negative exponent becomes positive if I flip the t to the denominator, and then that 1/2 could become a square root again. So really that expression that I just wrote, the 1/2 t to the negative 1/2, is equivalent to 1/2 root t. Just to save space over here, I'm not going to rewrite the whole thing. t e to the 4t, well, let's see. This consists of a product of functions, so product rule, and then also inside of the exponential, I've got a 4t, which means I've got a composition. Composition tells me that I'm then going to use the chain rule. So the derivative of t e to the 4t would be the derivative of the first factor, which is 1, so e to the 4t, so 1 times e to the 4t, and then plus t multiplied by the derivative of the second factor. Using the chain rule, a 4 is going to come out, and then e to the 4t. Once again, I could clean this up by rewriting t times 4 as 4t. I could factor out an e to the 4t, but I'm just going to leave it as that just to save a little bit of space. And then the derivative of tan inverse, 1/1 plus t squared. Okay. So computing derivatives of vector valued functions is pretty straightforward if you're comfortable with Calc 1 derivatives, just all the different differentiation rules. In subsequent videos, we will use derivatives of vector functions to do lots of things, but this is just the basic idea behind it. Thank you for watching, and please consider subscribing.